Welcome to The Explainer, presented by Forge College. I am absolutely thrilled to have you back. Now, in our previous lesson, data allocation and persistent accounts, we laid down the foundational concrete. We learned exactly how to allocate space, set rent exemption, and use PDAs, program-derived addresses, to give our programs deterministic control over storage. So today, we're grabbing our hard hats and diving straight into the architectural schematics of advanced execution. We are going to connect those account-level mechanics to Solana's transaction model, focusing specifically on how durable nonces completely change the way you shape transactions for vault-like contracts. Okay, let's dive into this. All right, here is our literal blueprint for today. We'll be covering 1. The blockhash problem, 2. The durable nonce, 3. Atomicity and race conditions, 4. Vault initialization workflow, 5. Transaction shapes, and finally, 6. Key takeaways.
Section 1. The blockhash problem. To truly understand why we even need advanced tools like durable nonces, we first got to look at the constraints of Solana's default transaction model.
So, the core of our challenge actually lies in the recent-blockhash. Normally, a standard transaction includes this blockhash as a sort of freshness token. It basically forces you, the signer, to submit your transaction almost immediately. I like to think of the recent-blockhash kind of like a rapidly melting ice cream cone on a ridiculously hot summer day. You have a very short window, just a handful of slots really, to enjoy it, or in this case, to get your transaction processed synchronously. It's great if you're sitting right there and pressing send, but on the flip side, a durable nonce is asynchronous. It allows for deferred execution. It completely separates the act of signing a transaction from the act of actually submitting it to the network. So yeah, no melting ice cream. Section 2, the durable nonce. Let's formally introduce the hero of our temporal heist here. Formally speaking, a durable nonce is basically a time-stamped claim ticket. You create or borrow a nonce account that holds a durable value alongside a separate authority that can advance it. So instead of relying on that melting recent-blockhash we just talked about, the transaction header actually points to this nonce. Think of it exactly like a golden movie ticket. You go up to the cashier, you lock in your intent, and you get your ticket. But you don't actually have to watch the movie right this second. A relayer, acting on your behalf, can take that pre-signed ticket and submit it much, much later when it's actually time for the show. This is absolutely critical for off-chain services, scheduled operations, or multi-step vault flows where we just literally cannot rely on a short window blockhash constraint. Section 3, atomicity and race conditions. Because, of course, in any complex engineering schematic, what happens when things get a little chaotic?
Right, so what happens if two actors present a ticket for the exact same seat? Because the nonce account state actually changes when it's consumed, or, punched like a movie ticket, multiple pre-signed transactions referencing the exact same nonce are not all valid. Now, the Solana runtime provides atomicity, meaning a transaction either fully succeeds or it fully fails. But if multiple relayers try to advance the same nonce simultaneously, well, we get single success semantics. Only the very first transaction to be processed is going to succeed. The second one? The runtime essentially acts as a ruthless theater bouncer and just outright fails it because the nonce has already been advanced. In the context of a vault, this can lead to some really messy race conditions around deposits and withdrawals unless we design explicit, strict sequencing.
Which brings us to Section 4, Vault Initialization Workflow. Let's map out a safe workflow for this, shall we? So, how do we prevent the bouncer from ruining our night? Let's build our vault step by step. Step 1, we create and reserve storage. This allocates the PDA and transfers the rent exemption LAN ports. And this step is synchronous. You want the signer present right now. Step 2, we initialize a guardrail. We write the initial data layout and set an explicit state marker to initializing. This is super vital so our program can detect partial progress later on. Step 3, here is where the magic happens. We fund the vault via a relayer using a durable nonce. The user signs a transaction to transfer tokens into the vault referencing the nonce. A relayer holds on to this and submits it later. Finally, step 4. We finalize initialization. We run validation checks, confirm the expected balances, and set that explicit state marker to initialized. Walking through this step-by-step schematic shows exactly where we rely on immediate synchronous execution for the setup versus where we leverage deferred durable nonces for the user funding. Section 5, Transaction Shapes. Let's zoom in on the exact placement of our instructions. Okay, the shape of your transaction dictates everything here. In a synchronous, create and initialize setup, we don't even use a nonce. It's an all-or-nothing, totally retry-safe transaction. But consider a pre-signed deposit, where we place the nonce advance instruction early in the transaction array. If we do this, the runtime advances the nonce first. Now, if a downstream instruction, like, say, the actual token deposit, fails, the nonce is still completely consumed. Your pre-signed retry ticket is now invalid and totally shredded. So what if we put the nonce advance instruction late or last? Well, this might preserve your ticket if the deposit fails early. Actually, scratch that. It's incredibly complex to architect because the runtime often requires the nonce instruction to be present early for freshness validation anyway. The big takeaway here? Placing the nonce advance instruction early versus late completely changes your rollback assumptions, and it requires some very deliberate planning.
Section 6. Key takeaways. Let's wrap up our blueprints.
All right, here are your 3 golden rules. First, treat durable nonces as a finite resource. If you've got a ton of users depositing, plan a per vault or per operation nonce strategy to completely avoid those messy race conditions we talked about. Second, use idempotent initialization. Build explicit state markers, like uninitialized, initializing, and initialized, so your program can safely detect partial progress and recover if a multi-step flow happens to get interrupted. And third, be hyper-deliberate with the sequencing and placement of your nonce advance instructions, simply because that position dictates whether your users can safely retry a failed transaction or if their nonce gets burned for nothing. Next up, ERC 4626 concepts and mapping to Solana. As we prepare to transition these core execution patterns into our next lesson, we're going to take all these concepts on atomicity, signer coordination, and persistent storage trade-offs and use them to construct industry-standard vaults. But I want to leave you with a thought. If durable nonces decouple time from execution, what happens when the underlying state of your vault completely changes before that ticket is ever punched? Think about that as you start sketching out your own vault instances. Thank you so much for joining me for this explainer presented by Forge College. Remember to visit forge.college to further master the Solana virtual machine and explore more deep dive Web3 educational resources. I'll see you in the next lesson.